I recently saw this Tumblr post about the shaky shake of Pokeballs and immediately wondered two things. One, what does any of this mean? And two, why would Game Freak make this so complicated? Well, in order to understand the secretly genius reasons Game Freak did all this math, we first have to break down what it all means. Pokemon catch rate calculations vary between generations, games, areas, and Pokeballs. Lots of different equations have been used throughout the franchise. But today, we're only focusing on this one. This is the shake calculation for the mainline games in Generations 3 and 4, outside of the Safari games. When you throw a Pokeball in Gens 3 and 4, 4 shake checks are performed. The way a shake check works is the game generates a number between 0 and 65535. Let's call that number x. The game then determines the value of the shake equation, let's call that value b, based on the modified catch rate of the Pokemon, which we'll call A. If X is less than B, then your Pokeball will shake and another check will be performed. Essentially, you check, shake, check, shake, check, shake, check one more time, and the Pokemon is caught. However, if X is greater than B in any one of these checks, the Pokemon will escape. But why does the check use 65535, a seemingly random number? We humans like to work in decimal, base 10. In each number column, or digit as they're called in base 10, we can store 10 possible values, 0 through 9. With 2 digits, we can store 10 times 10, or 10 squared values, 100 values. With 3, we can store 10 times 10 times 10, 10 cubed, 1000 values. Let's make a general equation. The amount of possible values we can store is equal to b, that's our base or radix, in this case 10, to the power of c, that's our number of columns, in this case digits. If we have 3 digits, we can store 10 to the power of 3, or 1000 possible values. The largest possible value we can store in C columns is b to the power of c minus 1. So, the largest value we can store in 3 digits is 999. This is because the first value is 000. Unlike us humans, computers work with information in binary, base 2, ones and zeros. This is because they're electronic. So a 1 is on and a 0 is off. Our equations work here too. With 1 bit, we can store 2 values. So with 2 bits, we can store 2 squared, or 4 values. With 8 bits, also called a byte, we can store 2 to the power of 8, or 256 values. That means the largest number we can store in a byte is 2 to the power of 8 minus 1, or 255. Computers like to store data in one of a few sizes. A single bit, 4 bits, called a nibble, 8 bits, called a byte, 16 bits, called a short, 32 bits, called a word, or 64 bits, called a double, or long. Notice anything about the length of these values? They're all powers of 2. This is because computers don't just store values in binary, they also use binary to specify how many bits a value uses. Let's go back to 65535. This value happens to equal 2 to the power of 16 minus 1. That means this is the largest number that can be stored in a short, or 16 bits. Now that we understand a bit about binary, we can take a look at our shake equation. Let's start by factoring the first equation to get the second one. Our numerator, 1,048,560, is equal to 65535, that's 2 to the power of 16 minus 1, times 2 to the power of 4. The number in our denominator is equal to 255, that's 2 to the power of 8 minus 1, times 2 to the power of 16. A fourth root is just another way of writing a power of 1 over 4, so let's write that instead. Okay, now that we've rewritten our equation a bit, let's start rearranging. To start, we can separate our denominator thanks to the power of a quotient and power of a product rules. Next, we can multiply by the fourth root of a divided by the fourth root of a, because that all equals 1. And that allows us to move a into the numerator. Next, using the power of a power rule, we know that the fourth root of 2 to the power of 16 is 2 to the power of 16 over 4, so 2 to the power of 4. The 2 to the power of 4 in the numerator and the denominator cancel out. Let's rewrite this with fourth roots again, and take a look. We arrived at our second equation. Going from equations 2 to 3 is much easier. All we have to do is rewrite it so 2 to the power of 16 minus 1 is in front of our fraction, then use the power of a quotient rule to merge our numerator and denominator under the same root, and we're done. I'm going to rewrite this a bit so you can see the significance of these numbers. Here, we have 65535, the largest number we can store in a word, and 255, the largest number we can store in a byte. Now, we want the game to generate a random number x between 0 and 65535 that's less than the result of this equation b. That means the higher b is, the better. B is determined by the value of a, which is the modified catch rate of the Pokemon. We want a to be as big as possible because the bigger a is, the bigger b is. That is to say, a is directly proportional to b, or a alpha b. We calculate a using this equation here. We can better understand our shake equation if we find the range of a, that is, what values a can take. Let's start with this section. In the best case scenario for catching a Pokemon, you have it at 1 HP. But let's just pretend it could have 0 HP for now. It will make this much easier. We would have 3 times max HP minus 0 over 3 times max HP. That's all equal to 1. That means the result of this function is less than, but not equal to 1. We specifically use not equal here because remember, a Pokemon can't actually have 0 health, so we will never quite reach that value. Okay, what's our worst case scenario? Well, that would be a Pokemon with full health. In that case, HP max equals HP current. That would mean we have 3 times HP minus 2 times HP over 3 times HP. That equals 1 times HP over 3 times HP, which equals 1 over 3. That means the result of this function must be greater than or equal to 1 over 3. Next, let's look at catch rate. Each Pokemon has an integer catch rate value between 3 for hard to catch Pokemon and 255 for easy to catch Pokemon. Next up is ball bonus. This is a multiplier applied based on the type of Pokeball you're using and if you meet the criteria for its catching bonus. The lowest value is 1 for things like Pokeballs, Premier Balls, and balls for which you don't meet the bonus requirements. Now, about the highest value. This is a lot more complicated than you might think. See, Apricorn Balls in Heart Gold and Soul Silver use a slightly different equation. They apply their bonus directly to the Pokemon's catch rate, but still cap that result at a maximum of 255 and a minimum of 1. We can pretend Apricorn Balls don't exist for now, because their ball bonus is effectively always 1, while their highest value for catch rate is still 255. So, looking at the rest of the Pokeballs, the highest ball bonus you can get is 4, by using a timer ball at turn 30 or higher, a quick ball on turn 1, and technically a nest ball on a level 0 Pokemon, if such a thing were possible. Finally, we have the status bonus. This one is easy. We have a 1 for no status, 1.5 for paralysis, poison, and burn, and 2 for sleep and freeze. So now we can find the range for A. For an example of a worst case scenario, we can use a standard Pokeball on an unimpaired Azelf with full HP. That gives us a value of 1. For an example of a best case scenario, we can use a timer ball on turn 30 or higher on a frozen Bidoof with 0 health. That gives us a value of 2040. But there's a bit of a problem. If the value is 255 or greater, then the catch automatically succeeds every time. No checks required. That means the range for A is actually all integers greater than or equal to 1, and less than or equal to 254. Back to our shake equation, we now know its domain. In this case, that's the range of A we just found. Now, let's find the range of this function, or what values B can take. Let's remove this fourth root just for demonstration purposes. For the lowest value of A, 1, this section is a value that's very close to 0. That gives us a final result that's very close to 0. For the highest value of A, 254, this section is a value that's very close to 1, which gives us a result that's very close to 65535. Take a look at that. The range of this function is effectively 0 through 65535. That's also the range of x, our random number. Now, here comes the genius of this equation. Adding the fourth root back in won't actually change our range at all, because the fourth root of 0 is 0, and the fourth root of 1 is 1. So why include it at all? Well, take a look at this graph. This is a graph of our function without the fourth root. We want to generate a value that's less than b. That means if we land below the line in this half of the graph, we get a shake. But if we land up here, above the line, the Pokemon escapes. Now, take a look at the graph with the fourth root. Now, our chance of catching the Pokemon got much better. The fourth root manages to keep the range the same, while giving the player a slightly better chance to catch the Pokemon. Changing the value of this exponent changes this graph as well, raising and lowering the catch chance. Essentially, this single exponent serves as an easy way to make catching slightly easier or harder, based on how frustrating versus rewarding the designers felt catching should be for the player. It's a genius example of the intersection between player psychology and math in video games. I hope that made sense. If you made it this far, please consider dropping a like and getting subscribed. If you have any questions or corrections for me, please leave them in the comments below. I've been Solderpup the modded Doggirl. Thank you for watching. I'm just gonna hang out while the end cards are on screen. Look at that one. Look at that one too. That's pretty cool.